Now I'd like to do section 9.2, number 47. Like I promised earlier, this is another example of an identity. And in this case, they want you to prove the identity tangent of x plus pi over 4 is tangent of x plus 1. And they don't put parentheses around their x all the time, and I'm also guilty of that, but they don't mean the plus 1 is inside the tangent parentheses. They really should put the parentheses to make it clear. And then they have 1 minus tangent x. So in this case, the rule of thumb from earlier of starting with the more complicated looking side is a good one, but it's kind of debatable which side's more complicated here. The right hand side certainly has more stuff going on, but the left hand side has this, the sum of two angles inside of the trig function. To me, in my experience, the left-hand side here is going to be more complicated because we're going to have to use the sum and difference identities right here to satisfy it. Going backwards with one of these identities is always worse than trying to go forwards with them, left to right. So I'm going to start with the left. So the problem is to prove the identity. Okay, so I'm telling you it's an identity. I'm not going to be asking you problems where I'm asking, is this an identity or not? I'm just asking you to prove them. So really I should call it a proof, but okay. I'm going to start with the left, and remember with identities you start with one side and then you do properties to arrive at the other. So this is tangent of x plus pi over 4. That's where I'm starting. Now, because I'm really focused on just these ones, I'm going to rewrite this in terms of sines and cosines. So tangent is sine over cosine, so I get x plus pi over 4 divided by cosine of x plus pi over 4. Now, each one of those are these two identities. So I'm going to apply those identities now. So on the top and on the bottom, I'm taking alpha equal x, beta equal pi over 4. So in the numerator, I get this expression, sine x times cosine of pi over 4 plus cosine x sine of pi over 4. And in the denominator, I'm going to expand this cosine of a sum. So I have cosine x cosine of pi over 4. In this case, I get a minus sine x sine of pi over 4. Now, I don't need these identities anymore for this problem. I've used them. So let me cover those up, and actually let me move them out of the way. And let me now talk about the rest of the problem over here a little bit. So we're having to evaluate sine and cosine at pi over 4. Well, that's one of our standard points on the unit circle right here, and it goes with angle pi over 4. So I'm just going to use that to calculate the sine and the cosine at pi over 4. Both of them are root 2 over 2, as you can see. So this expression is really just sine x times root 2 over 2 plus cosine x times root 2 over 2 divided by cosine x times root 2 over 2 minus sine x times root 2 over 2. As far as I'm concerned, that's a perfectly good final answer. You could clean it up a little bit, but I think that's good enough. So that's number 47. Oh wait, no, it's not good enough. We have a goal here. We have an identity we're trying to prove. My apologies. So what do we do now? Well, the problem is, look here. We have a plus 1 and we have a 1, and there's no root 2's going on. So the first thing we should do is make those root 2's go away. So what I'm going to do is I'm going to move over here just to give myself some more room. And I'm going to factor the root 2 over 2 from the first term. And I'll be left with sine x plus cosine x. And I'll do the same on the bottom. I'll factor that root 2 over 2 out. And I'll be left with cosine x minus sine x. So at least that gets rid of those things. But we're still not really done. If you look here, you have tangent x plus 1 and 1 minus tangent x. And I don't see how I'm going to get a tangent here. Well, it's not clear how you're going to get a tangent. Now, with identities, it's okay to stop and maybe start from the right side and then try to get to the left. That's a perfectly valid strategy. And I'll let you try that yourself, and you'll see that you'll arrive here without too much trouble. What I'm going to do is I'm going to what's called multiply by a convenient form, convenient form of 1. Now, it's going to feel like I'm pulling this out of thin air, and I sort of am, but if you think about where you're trying to go and where you are, it starts to become clear sort of what you need to do. The sine here needs a cosine on the bottom to become a tangent. And if I had a cosine, 1 over cosine in that numerator, that cosine there, right here, would become a 1. So if I could get a 1 over cosine on the top, I would get the correct numerator. If I had a 1 over cosine in the bottom, this cosine becomes that 1, and that sine would become that tangent. Neat trick. So the fact is that 1 is equal to 1. I don't have room. Let me put it right here. 1 is equal to 1 over cosine x over 1 over cosine x. So because anything itself is equal to itself times 1, I can say that this expression is equal to this expression times 1. This is a lot like when we were converting units. And then I make the conscious decision to write that 1 in a convenient way. So it's this. And now I'm going to rewrite 1 like this. And I can do that. Equals are equals. So 1 over cosine x over 1 over cosine x. That's great. And now I'll get, if I multiply that in, I'm going to go right here for this. I'll get sine x over cosine x plus cosine x over cosine x divided by cosine x over cosine x minus sine x over cosine x. And at this point, I will end up with what I'm interested in. Sine over cosine is tangent. Cosine over cosine is 1. Cosine over cosine is 1. And sine over cosine is tangent. And that will complete the proof of that identity, because that's where I ended up at the end of it. So like I said, these are slightly more complicated identity problems, but the fundamental principles from earlier will still carry you through. Okay, so let me do one more of these. This next problem is a good one especially for people going into calculus. In calculus, you'll compute something called a derivative, and in calculus, this is an important problem for that. So, example, this is like number, what number is it? Number 51, okay? So I did assign 51, but this is a similar looking problem. It says prove the identity, and then in this case it's sine of x plus h minus sine of x over h equals, and I should get it's equal to sine x times cosine of h minus 1 plus sine of h cosine x. And then all of this stuff is over h. So that's a complicated looking expression, but it is an identity. Now, why is this useful in calculus? The left-hand side, if you've had any calculus at all, you might see that this is somehow related to what's called the derivative in calculus. Calculus is all about the expression 0 divided by 0. So in a calculus class, you'll plug in h equals 0 in some way. Not really plug it in, but sort of. And if you did that, you would see that you get 0 over 0. That process of getting a 0 over 0 and making sense of it is the heart of calculus. So this expression would be what you use in calculus to get what's called the derivative of the sine function. And that's one of the most important things in all of calculus. So, this is a baby step in that direction, but one of the most important things you'll see in such a class. So, relevant to this section is this top term here, this sine of x plus h. That's this identity here. So we're going to first calculate that and use that to simplify. So here's the solution. So start with the left side. Again, my advice from earlier about picking the side with a sum inside the parentheses as the more difficult side is a good idea. Okay. Now I'm going to pick the. I could have folded this the whole time. Live and learn. So I'm going to pick the side of. I'm going to pick alpha equal x and beta equal h in this identity up here. Okay. So this is going to give me sine of alpha cosine beta. So sine of x cosine of h plus cosine alpha sine beta. So that'll be plus cosine of alpha, which is x, sine of beta, which is sine of h. Then this minus sine x term comes along for the ride. And then all of this is over h. Now we're most of the way to this right-hand side, but there's this thing in parentheses here that's it's essentially factored. So we have a basic factoring situation, which is really just the distributive law backwards. I'm going to factor out. So this way is called factoring, and then this way is called distributive law. Okay, but they're both the same process. So what I have here are two terms that have a sine x in them. It's this term and this term. So I'm going to factor out that sine of x from those two terms, and I'll be left with, for this term, a cosine of h, and from this term I'll have a 1 left over. Because when you factor, you're multiplicatively removing it. So you're left with what's called the multiplicative identity. You're left with a 1. It doesn't become 0. Okay. Notice if I distributed this in with the distributive law, I'd have sine x times cosine h, that's that term, and I'd have sine x times minus 1, and that's that term. Now, this term just kind of comes down for the ride. It's cosine x sine h all over h. And that is exactly what I was trying to arrive at. Now in calculus, what happens at this point is you would learn, so just an aside for those going on to calculus, you have these formulas that are called limits, and it would say that the limit of this is 0, and the limit of this is 1. So when you do this, what I call a process for where you get a 0 over 0, this one will turn into a 0, and this one will turn into a 1, and you'll be left with the what's called the derivative of the sine function, and this will be the cosine function. And that's one of the great formulas of elementary calculus. Um, it tells you that the rate of change of the sine function is actually the cosine function, which tells you things about how the cosine function wiggles and how its wiggling is related to the sine function and vice versa. Okay. You don't need to know calculus for us, but for many of you going onwards, you will see this again.